Hey, welcome back everyone. So my name is Zach Vines, and what we're going to go over today is how to calculate a chi-squared test statistic, specifically when we have a situation where we're dealing with a contingency table. So these are going to be known as bivariate test statistics. There are such things as univariate test statistics, but what categorizes this as a contingency table is we essentially have some data that's organized by two different dimensions, and you can basically put it in a table organized by cells that compile and kind of cross over multiple different categories of data. So we'll show an example to make that a little bit more clear, but for right now I just want to talk about what the overall formula for chi-squared is, the overall steps you take in doing these, and we'll wrap up with a quick example at the end. So to start off with, chi-squared is what looks like when maybe you're first looking at it, just x squared, but that little chi symbol right there is kind of a funky x, so keep that in mind. So that is chi-squared right there, and the formula for it is simply the sum of every observed frequency minus each expected frequency. That difference is squared, and then you divide that by each expected frequency. So that sum of right there means that we'll have multiple situations given this table where we'll have to fill out this formula, and you do that formula for each of those cells and comprise it into a final chi-squared. So the observed frequency, what that means is that when we conducted our sample, the observed frequency is actually what we observed. When we went and we did our sample, we get some information, we write that down based on our observations. That is designated by the observed frequency. Whereas the expected frequency is just based on the natural probability you would expect to happen given the situation at play, is what we would find for the expected frequency. There's a specific calculation we'll do to find those expected frequencies, but the observed, that's going to be provided to you. It's from the actual sample itself. So I'll just very briefly go through this. I greatly recommend writing this down because these are the exact steps we're going to go through during the example we'll go through in just a moment. But for the first step, we'll have a contingency table set up like this, where we have some characteristics, x and y, and then other characteristics, a different x and a different y. So that's very theoretical in nature. The example we'll show will kind of help you tie your head around a more tangible situation. But you have data arranged by column and row, where there will be numbers in each of these right here that will be your observed frequencies. So the first thing you do is, when these numbers are in here, add your columns down and get your column totals, add your rows across to get your row totals, and then your row totals and your column totals should compile to the same overall total. So that is step one. The next thing you do is that you find your degrees of freedom. And the way you find degrees of freedom for a contingency table in a chi-squared situation isn't simply just n minus 1 like you may have seen in previous situations, but it's its own specific formula where you take your number of rows minus 1 times your number of columns minus 1. And you'll see in a moment what's really useful about the degrees of freedom right here is that for us to find our expected frequencies, we're going to have to do a certain number of probability calculations. But once we have a certain number of those probability calculations, you can actually just plug the rest of the figures without having to redo several calculations. Again, you'll see how that works in the example in just a moment. But the degrees of freedom tells you the minimum number of those probability calculations you're going to have to do, so you can simply plug the rest of your expected frequencies. So keep that in mind. It's very useful to know. The way you do these probability calculations is simply when you're looking at a cell, so let's say we're looking at XX, you take the probability that one of those characteristics happens. So let's say, this is like this first x right here. You'd find the probability that that x occurs and multiply it by the total of the other x. Again, you'll see that in just a moment how that works for an example, but that's how you find each of those EFs. You can simply plug the rest of them once you've done the minimum number of those calculations based on your degrees of freedom. And then finally, once you have each observed frequency and their respective expected frequencies, you simply plug that into the formula for every single cell. That's really the only tedious part about all of this, is just having to plug and chug that entire part, especially depending on how complex your contingency table is. But without any further ado, let's get into one example. Have these written down. This is exactly what we're going to be doing to make this video short and sweet, so check it out. Okay, so now we're going to put those exact steps that we just laid out into play for this example right here. So to start off with, on the top left over there, what's labeled 1, that is the information we're given. So clearly we have a situation here where we're talking about several different college majors, it looks like in the School of Business. We have accounting, marketing, finance, and economics. And we're breaking down the number of those students based on whether or not they are a male or a female. So we can maybe see whether or not a certain major tends to be male dominant or female dominant, and just see what data comes about. And so kind of the way it's organized, we can see that accounting majors who are male, there are 20 of them. Accounting majors who are female, there are 10 of them. And all of that's compiled through right there. So one thing is that these row totals and these column totals are not going to be given to you at first. So the only information you're actually given from the get-go is the information within the table itself, the 20, the 10, the 15, the 5, so on and so forth, and then the labels themselves. So the first step, remember, was to add the rows across and the columns down. So I did 20 plus 10 is 30, 15 plus 5 is 20, so on and so forth, got all of these row totals. Then I added all of the males up to get 95, all of the females up to get 55. When you add the column totals together, it gives you 150, which should match up with the row totals you add together, all of which is going to equal 150. So now you have everything laid out so you can continue on with the second step. So one quick thing I want to point out again is remember, what we are provided in the chart to begin with are your observed frequencies. They're what's given to you, it's what was observed when we conducted this sample. Now what we're going to do is lay the framework so that we can do our probability calculations, which are going to tell us the expected frequencies, which instead of us saying, okay, we found 20 male accounting majors, we would say, okay, given the natural probability at play with this situation, what will we expect for the number of male accounting majors to be? Then we can compile that into the final formula. So the second step was to find your degrees of freedom, so you know the minimum number of probability calculations you have to do, so you can simply plug the rest of the expected frequencies. So that's simply R minus 1 times C minus 1, where R is the number of rows in the table, C is the number of columns in the table. So here we have 4 rows of information, accounting, marketing, finance, and economics, so 4 minus 1 times only 2 columns worth of information, so 2 minus 1 is 1, we have 3 times 1 equals 3. And once you have your degrees of freedom right here, it tells you the minimum number of probability calculations you have to do so you can simply plug the rest. So before we start talking about how I did these probability calculations, let me show you the goal right here. So I have to do 3 of these calculations, and what I'm trying to do is to fill out this chart in such a way to where if I have these expected frequencies are going to be circled right here. So you can see the observed frequencies are just copied right over, and what I have circled is the completed expected frequency table. But what I want to do when I'm filling that out is to fill out enough of them so that I can simply add the rows across to equal these totals over here and add the columns down to get the column totals. So for instance, if I have that this was 19, which I did the calculation here, we'll get to that in a moment, but once I have that this answer is 19, I know that the expected frequency for this cell has to be 11 because 19 plus 11 is going to give me 30. So when you fill out a minimum number of those expected frequencies, you can just go, okay, well in order for this, for instance, if I had this 32, what would make it equal 50? This would have to be 18. To get to 20 from 13, what would this have to be? 7. And you just continue to do it like that. But you have to have enough of them in the first place so that you can plug the rest. So here's what we do. The way I worded it on the examples when we first started was it's the probability of one of the characteristics times the total number in the other characteristic. So for instance, I know that if I have to do 3 calculations, 3 probability calculations, if I did it for these 3 cells right here, then I could plug this one across to get 30, this one across to get 20, this one across to get 50, and once I have these 3, I can simply plug these down to get my column totals. And so when I've solved for this one right here, what I did was I said I took the probability of one characteristic. You don't have to choose one or the other. Sometimes you can save yourself a little work by choosing a specific one. You'll see what I mean in a second. But what I chose to do right here is that for this column to be the total number of males, I said, okay, let me find the probability of being a male for this situation. And I said that there are 95 males total out of the entire sample. We have 95 males out of the total of 150 people. So the probability that you are a male is a 63.63 repeating % chance. So what I did to find this was I took the probability of being a male and I multiplied it by the total number of accounting majors, which is 30 accounting majors. So it's pretty much saying if there is a 63% chance that I am a male and there are 30 accounting majors, I would naturally expect for there to be 63% of those accounting majors would be the number of male accounting majors. So we came up with 19. So you can see that when I chose these 3 right here, because they all fall in the male column, it made perfect sense for me to say, okay, when I want to do the probability of one characteristic times the total number in the other one, let me just do the probability of the characteristic that's going to stay constant for these calculations, so I don't have to do a new probability calculation every time. So you can see I took that same probability of being a male, but in order to find this cell right here, which would be the marketing majors, I took the probability of being a male times the total number of marketing majors. And you're going to get a rounded number right here. Sometimes it's okay if you round it to a whole number since we're talking about people here, you know, males or females being what a certain major. But if you want to be perfectly precise with your answer, you should probably put the full decimal point. I just rounded for simplicity's sake for right now. But we get 13 for right there, so I fill in 13. Finally, that same probability of being a male times the total number of finance majors will be 32. So I plugged in 32. So in just a moment, we'll segue into how we actually fill out the formula, but you want to have this written down and understand that because we did these 3 probability calculations, we understood that, okay, I can plug this 11 across to get 30, this 7 across to get 20, this 18 across to get 50, so on and so forth. So I didn't have to do a probability calculation like this for every single cell, so it saves us a lot of time. So you have to have this written down because what was given to us originally are your observed frequencies, everything we just calculated are your expected frequencies, and the formula for chi-squared was the sum of, you know, so for every situation, the expected minus the observed squared divided by the, I believe, is the expected. So let's get into how we do that calculation to wrap everything up. Okay, so now we're just taking the information we had from this table, so I didn't even erase it, it's exactly where it was, and we're just plugging it into the chi-squared formula. So again, the chi-squared formula is your observed frequency minus your expected frequency, that squared divided by your expected frequency, and you do that for every single cell you have in your contingency table. So I laid out everything right here where I basically just went in a certain order, took each cell, so let's just start with the 20 minus 19. I took my observed frequency, so what actually happened, what was originally in my contingency table, subtracted out my expected frequency that I got from my calculation. In other situations, it's what you got from when you just plugged it across because you did enough calculations to where you could just plug them. And it's 20 minus 19. I squared that and I divide it by the expected frequency of 19. And I simply do that for every single one of these cells. So I do 15 minus 13 squared divided by 13, 30 minus 32 squared divided by 32. So like I said before, this is the most tedious part of it for sure, where it's literally just every single cell that you have, you're just plugging into it and you're doing these calculations manually. But you can see that for each of these, I came up with the actual value of them. So 20 minus 19 squared divided by 19, I got, and these are all going to be pretty rounded, but about 0.53. I do that for every single one. You add them all up, and that gives you your chi-squared value. So you can see that as long as you have those steps laid out, where you start off by adding the rows across, the columns down, getting your overall total, do your degrees of freedom calculation so you know the minimum number of those expected frequency probability calculations to do the minimum number of those calculations. Just be smart to do the ones that you could do so that you can simply plug the rest of them, plug into the formula, and you're good to go. So thank you so much for watching, and I hope that helped.